the problem of the day, which is minimum operations to connect hospitals. So this is a medium problem, but I think if you have done uh, graph problems, this can become very easy. So let's see what the question says. You're given an undirected network of V hospitals numbered from 0 to minus 1, represented as a 2D array edges, where each edges is U to V, denotes a direct connection between hospital U and hospital V. In one operation, you are allowed to remove any existing link and reconnect it between two hospitals that are currently not connected. Your task is to determine the minimum number of operations required to make sure that all hospitals become connected, either directly or indirectly, using the given links. So, what the question basically says is that, so let's say there are n is let's say 5. So you have four hospitals, 0, 1, 2, 3, 4, and then you're given some links on these. So let's say 0 and 1 is one link. So 0 and 1, these are connected to a undirected edge. So 0, you from 0 you can go to 1, and from 1 you can go to 0. So let's say 0, 1 is one edge, 2, 3 is another edge, 2, 3 is another edge, and 3, 4 is another edge, 3, 4 is another edge, right? So now from 0 you can only go to 1, from 2 you can go to 3, and you can go to 4. So because this is not a direct connection, but this is an indirect connection, right? Okay, let's say you are also given 1 0 as another edge. So this is a back edge kind of, but this is not really required. Okay, let's say rather than 1 0, let's say we have 2 comma 4. So 2 comma 4 is an additional edge. Okay. So now what the question says is, in one operation you can remove an edge. So let's say we remove this edge from here, and let's say we add this edge here, right? Because see, currently with this setup, from 0 you cannot go to 3, from 0 you cannot go to 4. So this is not a connected graph, because for connected graph from one edge, you must be able to go to all the edges for all. Starting from any edge, you must be able to go to all the edges. From 0 you cannot go to 3, from 0 you cannot go to 2. But let's say in one operation, let's say we remove this edge from here and we add this here. So after doing this operation, now from 0 you can go to all the edges. Now from each, starting with each edge, you can do this operation. Like even you can see that the graph now is connected. Note this edge is not here, right? So if this makes sense, so what the question says is, find the minimum number of operations needed for this graph to become connected by doing this operation, and if it is not possible to make this graph connected, return -1. When would it not be possible? Let's say if this was the graph, any reassignment on this graph would not make this graph connected, because even if we remove this edge and add it here. Now this four becomes not connected. Okay. So how do you do this? So the first observation that should come to your mind is that the minimum number of edges required for a connected graph is actually v minus one. This is a three property. So a three basically is a graph only, which has just two properties. The first is that there are no cycles and no. So if there are no cycles on it, the graph would actually have v minus 1 edges. So v minus 1, we can see here 1 2 3 4 5 6. So 6, and the edges is 1 2 3 4 5. So 6 comma 5, this is v, this is v, right? So for the graph to be connected, the number of edges must be greater than v minus 1, or greater than equals to. So first we can check is the number of edges that we have. It is less than, if it is less than v minus 1, we should return -1, because either rearrangement would not solve a case. Okay. So first thing, this is explained. Now the second observation is that if they are more than v minus 1 edges, so here the number of edges was less than v minus 1, here the number of edges is greater than equals to v minus 1. So what is now the number of operations needed? Number of operations needed. See, so any graph is actually a collection of components of it, right? Collections of connected components of it. Let's say a graph is having these components. It is something like this, and let's say this also. Okay. So if the graph is this, so there's one component here, C1, one component here C2, and component here C3. So what can I say that what is if there are three components, what is the minimum number of new edges required to make all of these connected? You make all of these edges, make all of these components connected. So then we can say that we can mark this as like a graph which has three vertices, right? C1, C2, C3. And again, for this graph to be connected, the number of edges should be V minus 1. Here the V is 3, so you need two edges, and we can even see like, one edge here, this satisfies it. So the number of edges we need is number of, this is hash, number of edges is actually components minus 1. So we can get the components of the graph and then just return components minus 1. This is the number of edges we need, new edges we need. And we can also see that there are some extra edges, like these are extra edges here. These two are extra edges because see, this is already connected to this indirectly. We do not need a direct edge also. So this edge we can reassign to like this. Similarly, this edge can be reassigned to this. And there are some extra edges, and this is satisfied because of this property is satisfied that the number of total edges is greater than or equals to v minus 1. So hopefully this makes sense. Let's jump to the code. So what I've done is basically doing do the first check that if they are less than v minus 1 edges, the graph could never become connected. If this is the case, return minus 1. If it is not the case, I create an adjacency vector. I go over all the edges. I get the first vertex, the second vertex. I add the edge to adjacency vector. Then I get the components of it. So for that, I just do a like number of islands, basically problem solution. So create a visited vector, go over all the edges. If sorry, go over all the vertices. If this is not visited, start a DFS from it and add it to components. Finally, just need to return components minus 1. And a DFS function, it's a simple function. So yeah, mark this node as visited and go to all of its neighbors if it is not visited. Yeah, this works. We can also submit it. So, yeah, thank you for watching. If you like this video, subscribe, like it, all of those things. Bye bye. Thank you for watching.